welcome to another episode of the Data Science Decoded podcast. As far as I can count, it's number 29, but I might be wrong by one or something like that. So good to see you all. Hi, Mike. Hi, Nir. How are you today?
Hey, how are you? Good. We're doing good. I'm doing good.
I'm okay as well. I missed you guys. I'm not sure that this episode is number 29. I think it's
Oh,
number 28. And I think we have published 26 maybe. And we have one or two episodes which we said got some
that's true.
problems with sound. Yeah, you are correct. I'm wrong. It is 29 because we have 26 published episodes and two episodes with something that went wrong on my side of my recording app, some problem with my computer, maybe. I don't know. Now it is somehow it has fixed itself. I don't know how, but you're right. It is this episode number 29, and I hopefully will not have any technical problems as in episode 26 and 27.
Great. So I heard from someone that you might have had one drink prior to the recording. What would you say about that, Mike?
Yeah, I've got some whiskey shots. Nah, not too much. I was born in Russia, so I got used to drinking quite a lot when I was young. Now I'm too old for drinking in such serious amounts of alcohol. But still, it was a very good event of AWS, and got very good whiskey shots, something quite expensive, and some good food. So I ate a lot. I drink not too much, so I guess I'm gonna be okay. But
Perfect.
yeah, but if I say something stupid, don't be surprised.
So it's good that we have a more chilled back episode. And also, AWS are not a sponsor of the podcast, but maybe they should.
Yeah.
And
I can talk to
we're
them
gonna
about it.
approach them.
By the way, I can talk to them about it. So maybe
Yeah.
it will happen. But I don't. It is not a promise. It's just an intention.
Okay, cool. I'll remember that. So to our listeners on screen, it's the paper from 1877 with the title On the History of the Method of Least Squares, which is, of course, highly important to all of us. And it's by Mansfield Merriman, and he's a PhD from New Haven, Connecticut. So a little bit about Merriman. He was an American civil engineer, mathematician, and educator. So he contributed a lot to engineering, statistics, and mathematics. And specifically, he was teaching in engineering areas that related to mechanics and material science, hydrology, and of course, the mathematical aspects. So his key contributions, of course, this survey of the history. He also wrote a whole book from 1910, so like 30 years after this paper, about the method of least squares. And also other important topics. Let's see.
Daniel, some small remark. You can
Mhm.
see that in 1877, the least squares methods already got some history. So you can
Yeah.
just imagine how old is this method. So 140 years ago, this method, it's got a history. So it is really, really old.
Yeah, great point. And we all, throughout, let's say, our history, saw and used least squares. Before we start, I wanted to ask you guys, when was the first time you encountered the concept of least squares, if you remember?
Actually, I don't remember if it was the first time, but the first time, for the best of my knowledge, the first time in which I encountered this great method was, not surprisingly, in the optimization course which I took university, I studied in Moscow, and it was in 1996, I guess, many years ago.
Yeah, while
Oh,
drinking vodka.
yeah, yeah.
What about you, Nir?
I think it was estimation theory course, graduate studies. Joseph.
In grad school. Okay.
Yeah, grad school. Yeah, yeah.
Okay, so my
I knew about
experience
it
is
before.
different. Interesting.
I knew about it before. I used also Kalman filters before, but the actual proof and the actual derivation
Okay.
was only on
But when did you use it? Or somebody told you, yeah, you should minimize these squares without theory.
I don't remember. I don't.
Cool. So I remember, I'll tell you that
Okay.
my first semester of undergrad, so I also studied physics. And first semester, you take a lab course. And I think it's mostly like mechanics, and you do some experiments and you measure stuff. And of course, there's errors in measurement, etc. So they just showed us I think the equation, and said, okay, you need to run this and minimize this error. And I'm like, I had no idea what I was doing.
Yeah.
But I still remember to this day that it was something related to error and noise and stuff like that.
Yeah.
Daniel, what was less clear for you? The least square stuff in your first semester, or there's some epsilon delta stuff with the sequences? What was less clear?
You can guess. But at least they try to explain us the theory behind epsilon delta and limits, and this relates to our previous episode about Cauchy, right? He did rigorous proof with epsilon delta for limits.
Yeah.
That's a good point, Mike. And
Good point, Mike. Good point. Yeah, epsilon delta was a baseball bat to the head for sure.
Yeah.
Yeah.
By the way, for me, it wasn't too complicated because I studied such stuff. I studied in some advanced math class at school in the town I was born. It wasn't Moscow, so for me it wasn't shock. I wasn't shocked by that, but I remember that most of the students were really shocked. You know, you see it for the first time. You don't understand, you know, all this n, the big n and the small n, and this stuff less than epsilon and greater than delta. You know, but I can understand it, but I learned it, but I studied it at school a year ago.
So, and I want to dovetail also our previous episodes and how they relate to this one of least squares. So we mentioned Cauchy. Our first episode with Fisher, he defined the maximum likelihood, and we know that we talked about it, how it relates to least squares. The episode, I think, number 7 or 9, was about PCA. They use least square there in the dimensionality reduction. The one with Rosenblatt, the perceptron, there was least squares there. I think in the Monte Carlo episodes, there's least squares. Expectation minimization algorithm also. So many episodes are highly related to this one. Okay, so let's actually read the history. It's around 3 pages, so it's not long. I think we can cover most of it reading. So it starts by saying, it is the object of this article to present some brief notes concerning the various demonstrations of the method of least squares, with references to the original works or memoirs in which they were given. Sounds cool? The honor of the first publication of the method belongs to Legendre. How you say it, Neil?
Legendre.
Legendre. Perfect. My French is lacking. And he says, but I can read the next sentence in French. Listen, everyone. It is given in his work, Nouvelles méthodes pour la détermination des orbitaires des comets, which actually I can translate. It means novel methods for determination of orbits and comets. of comets, something like that. So again, it came from astronomy. Similar to the motivation of Cauchy, trying to solve probably some equations related to movement of stars. And he says that Legendre published it in 1805.
So this method is now 220 years old. I think it is one of the old methods we are using.
Yep.
And he says, in this work, the rule that the sum of the squares of the error should be made a minimum to obtain the adjusted values of observed quantities is proposed as a convenient method only. Okay, so he didn't do any rigorous proof. The rule for the formation of normal equation is deduced and applied in practical example. And he says also the arithmetical mean is shown to be a particular case of the method, and the analogy of the formula with those derived in mechanics for finding the center of gravity of bodies is noticed.
Yeah.
By the way,
so as we said.
Okay, well, guys, do you remember what is normal equations? There is some there is notion called normal matrix, but what are normal equations?
The normal equations is the least square is given. Let's say that our equations are overdetermined system of equations are y equals h theta. Okay, so the least square is h transpose h to the minus 1 h transpose y. Okay, the measurements. The normal equations are h transpose h times y equals h theta, or h transpose theta. And these are the normal equations, and we can actually solve the least squares right from there, or we can invert or pseudo inverse this h transpose h and solve it like that. But these are the base for the linear regression or least squares algorithm.
I see. Okay, cool.
And first, thank you, Nir. That was illuminating, and I also didn't remember that. But now I'll continue with a quote that he in French by Legendre, and I won't read it. It's quite long, but I have the translation to English thanks to ChatGPT, and it translates to: the method of the squares in a way reveals the center around which all the results provided by experience come to be arranged in such a way as to derive from it as little as possible.
Okay.
So again, he somehow compares the method of least squares to finding like the center mass of some body or some star.
Yep.
And let's see, it says here, meaning Merriman, although this can be scarcely be called a proof, it shows that Legendre fully appreciated the advantage of the method. And he says the first proof of the method of least squares was given by Dr. Robert Adrain in the Analyst, so also the same publication as this paper. And Adrain is the Analyst is an American journal edited by him during the early part of the century. So again, it's 1808, it says here. So it's like 80 years prior to this paper that we're reading. And he says the term least squares is not used, and Adrain seems to have been entirely unacquainted with Legendre's researches. So it's cool, like almost the same year, two different people derive similar tools, which is really interesting, meaning like there is some kind of cultural, social movement of technology and concepts, right? So even if some person is not, I don't know, coming up with some idea, most probably somebody else will come up with it. So that's interesting. It happens a lot. We have many examples in science when that happened. Yeah, Mike.
Yes.
But we should also take into account that it happened more than 200 years ago. So Legendre, I guess, lived in France, and Adrain lived in the United States.
America.
In the United States. So I guess they have no communication. So it should have been a surprise if he were aware about it. So in this period, with almost no communication, if you send some letter, I don't know how much time it took to for the letter to get from United States to France. I don't know, maybe 1 month. I don't know. Some pigeons. I have no idea. So we shouldn't be surprised that Adran didn't know about it. It is.
Yeah, for sure. We shouldn't be surprised during that times. Yeah, and just my claim is we always look back about history and specifically history of science and think, oh, this person was pivotal,
Yeah.
but most probably without that person, we would still come up with similar ideas.
Yeah.
There's many examples like Newton and Leibniz thought independently about different concepts. Einstein, and I forgot the name. I have a book about it actually, and let's see. Oh, here it is. Like science, a history. So it goes over a lot of similar concepts and ideas. Cool. So I'll continue. And he says the proof of the least squares consists in showing that the probability y of the error x is given by an equation of the form y equals c times e exponent to the power of minus h squared x squared, in which c and h are constants and e is the base of the neutral system of logarithm, a natural system. Yeah, which makes sense. That's what we do today. We assume that the error in our measurement has a Gaussian distribution.
Yep.
And then he continues, hence, by well-known rules, the probability of the system of errors, he now generalizes between x1 to xn, is the same as prior, but we have now a multiplication of all of those errors. So it's minus h squared times, and you open brackets, it's x1 to the power of 2 plus x2 to the power of 2, etc. Okay, that's what we do today as well. And then he says, and the most advantageous or most probable system will be that for which y is a maximum. And this requires that everything that is in the brackets is in a minimum.
The sum of squares, yeah.
Okay, why we want y to be maximum?
Maximum likelihood.
Oh, exactly. Right, but this paper is prior to maximum likelihood. So although he says here that's like the mathematical proof, it still has assumptions that he doesn't know about.
Yeah.
And he says that's why it's called the method. Whence it's called the method of least squares, because you have the squares and you try to minimize them. He says the proof by which the law of facility or probability of error, I don't know what facility means. Maybe that's how they called something back in the days. But it says facility or probability of error is established, cannot be discussed here. And it says it's analyzed and shows to be unsatisfactory by Glacier in some paper from 1871.
Okay.
Cool. And then it continues. The second proof was given by Gauss, the famous one that we talked also last episode, in his Theoria Motus Corporum Coelestium. I don't know. Well, I guess it's Greek or
That's
Latin.
Latin. Yeah. I don't know Latin, so I don't know the translation. And published at Hamburg in 1809. So also few years from Adrain and Legendre. So another unrelated derivation. It occupies pages, some 20 pages, and then it says, assuming that the arithmetical mean is the most probable value of a quantity directly observed, Gauss shows that the law of facility of error must be of the exponential form. So maybe it's like the probability of the error. I don't know what facility means. Similar as we said prior. So
Maybe.
again, here Gauss assumes that the arithmetical mean is the most probable value. So it's like estimation theory, right?
Yeah.
Again, Fisher. What did you say,
Yeah.
Mike?
Oh, I said that the facility may be density because we are talking about the Gaussian distribution.
That's what
so
they mean. Yeah.
It hasn't probability. It is density, not probability.
Yes.
Yeah. Thank you for the correction. And then he says this is the proof given in the great majority of books. Again, back in 1870. He continues, the assumption of the rule of the arithmetical mean impairs greatly its strictness. And as presented in Chavonet's treatise, also about astronomy, it is particularly illogical. The constant c being given some value so that the probability of error is a finite quantity. Okay, I don't understand exactly what they mean here. Did you understand, Neil?
Yeah, what they mean is just given the normalization constant c, so that the density will be the area under the density will be 1. Is some constant h times phi to the minus 1/2, which we already know, right? H is the is 1 over the variance, and that's it, basically. H is also in the exponent there, so
it's one of the constants.
Yeah.
Yes.
And he continues, the third proof was given by Laplace in 1810. So again, also Laplace is in the mix. In the Memoir Institute, France, something actually from 1809. And
1810, no?
Yeah, but here he says.
Okay.
So it's around 1810.
Okay.
And it is reproduced in his theory analytique de probabilité in some chapter. And it uses only the axiom that positive and negative errors are equally probable.
Yeah.
And it is independent of the particular form of the law of facility of error. Cool. So no assumptions about the density function, except that it has positive and negative values. And provided that the number of observation is infinite.
In other words, they're getting more and more closer to the Gaussian distribution.
Yes.
So Laplace got the closest to the Gaussian distribution from all these authors that were mentioned in this paper.
And he says it is the most satisfactory of all the demonstrations of the method. And he says there's another pages. Laplace also gives another proof called Laplace's second demonstration, and it depends on the axiom that the mean of all the errors taken positively must be a minimum to give the most advantageous value.
Well,
another proof there is by Gauss in 1823. And this proof takes for granted that the mean value of the sum of the squares of the errors may be used as a measure of the precision of the observations. It introduces no law of facility of error. So no assumptions about the distribution.
Exactly.
It says the proof is entirely untenable and has, we believe, only been followed by Helmert in 1872. The sixth proof was given by Ivory in 1825. Let's continue. The seventh attempt proof was given by Adrain in 26. The eighth proof was given in 1837 by Hagen in something which is German. Well, that's a long word. Who volunteers to read it? Neil, what do you say about this word here?
I have nothing to say about it.
It is too long to be read by us.
I think Mike needs like 5 more drinks and then you read it.
Yeah.
Let's continue. If there's another, the ninth proof is due to Bessel. We're all familiar with Bessel.
But in different context,
Yeah, of course. But again, a lot of players that we've heard in other places, and it was published in an article titled something really long in German again.
But also in astronomy.
Also, yeah, in astronomy in 1838.
Yep.
Let's see, the 10th proof was given in 1844 by Donkin, and he's from Oxford. I can read an essay on the theory of the combination of observations.
Mm-hmm.
11th proof, number 11, was given in 1850 by Herschel. He's from also the UK. 12th proof was given by Donkin again in 57. 13th is by Crofton. And let's see. Okay, he concludes. Although no one of these 13 proofs is perfectly satisfactory, yet each is valuable as setting the subject in a new light and illustrating the laws of thought which have led to the universal employment of the arithmetical mean, and no other rules for the judgment of observations. No discussion of their relative values can be attempted here. The critical papers of Ellis and Glacier quoted above may in this connection be mentioned as of great value to students of the theory of the subject.
So, guys, I have a question for you.
Mm-hmm.
If you were asked now to write such a paper about all possible proofs of the least square, how many proofs are gonna be in there? 30, 40?
More probably.
Probably a lot more.
Probably.
Listen, this is 65 years of, and we have 13 proofs. So in 250 years, I don't know, maybe 150 proofs.
Yeah, but in the 20th century, I think it was quite established fact. So I don't think that many guys, many mathematicians proved it in the 20th century. Maybe in the beginning. So I guess all these proofs came to the end in the beginning of 20th century. But maybe I'm wrong. I have no idea.
Yeah, interesting. I would say that I would guess, okay, that's my guess, that after Fisher's paper that we covered in the first episode, I don't think many came with more proofs because, in a sense, maximum likelihood generalizes.
Yeah.
By the way, Daniel, we can ask ChatGPT or some LLM, but how many proofs of the least squares exist? It's interesting what answer is going to give us.
Yeah, interesting.
I'm doing this live.
Yeah, do it. Do it live.
Yeah, live. Squares exist. Let's see if we're gonna get a hallucination or not.
But tell him it should give you
no. So now he starts with classical proofs from 1805 till exactly 900, 1900. Oh wait, a network error occurred. I wonder if it's trying to record our episode and there's some problems with my internet connection.
Yeah. Let's have the listener comment below. Search it up and and put it in the comments below.
Neil, you can give it to your students as a homework on one of your courses.
Listen, one of the modern proofs is Camero bound.
Mm-hmm. Yes.
Okay.
It proves that the least squares is an efficient unbiased estimator, and we covered that.
Yes.
Okay.
There's the maximum likelihood proof, which we also covered.
Mm-hmm.
There's a Bayesian proof, which I don't know. That's what he says. There's the convex optimization proof.
Okay.
But
how many? Tell him to summarize.
It says at least. He says at least 17. It's not really useful.
At least 17. Okay.
Yeah, it is.
Okay.
Yeah, a lot, right?
Yeah, it just emphasizes the fact how important it is.
Yeah,
It's crucially important in many
yeah,
areas of mathematics,
yes.
from control theory to
Mhm.
estimation, and now in machine learning and
Yep.
optimization, in many areas of mathematical analysis, least squares is crucially important.
Hmm.
It is
Hmm.
widely used till now, till these days.
Yes, 100%. And do you guys use it in data science, machine learning?
You know, you can, if you do some linear regression, and there are
Yeah,
some cases in which I did do it, and if you do some,
yeah.
random forest regression, or like GBM, or cat boost or XGBoost, and if that is not categorical but continuous,
That's it.
how do you estimate your errors? It's
Yeah,
just
exactly,
least squares,
exactly,
you
exactly.
know.
Yeah, yeah,
So I'm doing it a lot
yeah, yeah,
till
yeah,
now.
yeah, yeah, yeah.
Yeah, so in a sense, I would say we do it indirectly, as Mike said, because
Yeah,
we
yeah,
every
yeah.
time we solve an optimization problem,
Hmm.
most probably there is some least
Yeah.
No,
squares.
now nowadays we are coding also indirectly. I
Yes,
mean, I'm using cursor. I don't write. I'm not writing my code. Most of my code, except for some, some prints or loggings, and I think even these ones are written by cursor. So we are using it, most of the stuff we are using in machine learning today. We are using indirectly or via some prompt engineering.
yeah, it's true.
That's an optimistic way to end the episode.
Yeah.
So thank you. Thanks to you, the listeners, and we're gonna see you next time.
Bye bye.
All right, guys. Bye bye.
Bye.